In this presentation, we're going to look at some special equivalences, and we're going to look at some equivalents. We're going to look at some statements that it turns out aren't equivalent, where if you kind of go by what you learned in algebra, you might think they were. So this is going to kind of be a warning showing you that the rules you learned in algebra don't necessarily apply here. So let's start by looking at this distributive type property. Remember from algebra, the distributive property is the one that says you can take something outside the parentheses and distribute it to everything inside. And that's what I've done here. I took this P and I distributed it to the Q to get this, and I distributed it to the R to get this, and the or here in the middle just stayed the same. So I've written out the truth tables for the two sides here, and I did what we've done before. I did all the possible combinations of P, Q, and R. And I went ahead and filled in the P, Q, and R columns. These are the ones where you're just copying the values over from the base table, from the base columns. That way, you didn't have to sit there and watch me write 50 or 60 T's and F's over and over again. And that's going to let us focus on the ands and ors, the logical parts here, which is kind of where the action is. So if we look at this or, remember that or is false only when both of the inputs are false. And everywhere else, it's true. So now we can kind of disregard these input columns. And to get this and, I'll compare the P row with, the P column with this column. Now remember, with an and is true only when both of the inputs are true. So that happens here on row 1, row 2, and row 3, and everybody else has at least one false. All right, and that finishes this table with this row as our result. So now let's come over here to the other one. I'm going to start inside the parentheses where I have ands in both cases. And remember, this is the same thing we just did. I'm going to put true only in the rows where both of the inputs are true, and I believe that's all of them, just those 4. And then I'll put false everywhere else. Then I'm going to look at the and column, and I'm going to evaluate that using the values that I just wrote in. So, or. I'm going to look at this or column. And or is false only where only where both of the inputs are false. That happens here, everything from here down, really. And all of the others are true. And then if you compare this row, this column, to this column, you'll see that both of them are true on the first 3 rows and false everywhere else. So because the end results of the two tables were the same, we can conclude that the two original statements are equivalent. So this kind of distributive property does work with logical statements. All right, so let's look at another distributive type property. Here I've distributed this not, the negation, into the parentheses. Let's see what happens here. Again, I've filled in the P and Q columns already, so we can just focus on the logical connections. This and is true only when the inputs are true, when the two inputs are both true. Every place else is false. And then the negation just reverses everybody's value. False, true, true, and true. And so on this side, remember the negations are a higher priority, so I'm going to do those first. Reversing everybody's value. false, and true. And then I'm going to do the and in the middle. And the and is true only where both inputs are true. Everybody else has at least one F. Remember, I'm looking at these columns, not the P and Q columns, so it's these F's that tell me this one is a false. And now if we compare the result columns here, excuse me, wrong one. If we compare the result columns here, you'll see that they are definitely not the same. As a matter of fact, they're exact opposites of each other. So we cannot say that these two statements are equivalent. You cannot distribute a negation into parentheses like you could a negative sign in algebra. So kind of the rule here is you need to be careful. Don't assume that because something worked with an algebraic expression that it's going to work with a logical statement as well. So let's take a look at an example where you actually sort of can distribute a negative. This is a very well-known equivalence. It's one of what are called deMorgans laws, named after a very famous early researcher in the field of logic. And what I've done here is I've distributed the P into the parentheses to get these two terms. But look at what happened to the connector here. The and changed into an or. So you can, in a sense, distribute a negation into parentheses. You just have to reverse the logical operator. And let's confirm for ourselves quickly here that that's true. Here we have a logical and. That gives us these values. And the negation reverses all of them, so it becomes this. And over here, we'll do really what we did on the previous example. I'll reverse the values of the P and the Q. And then do the or this time. And an or is false only when both of the inputs are false. Everywhere else, it's true. And now you should be able to see pretty quickly. This column is the same as this column. So these are, in fact, the same. Now, there's there's actually two deMorgans laws. The second one is almost the same. It just reverses the and the or, not P and not Q. So that's a good example for you to try on your own. Work out the two truth tables. Confirm for yourself that that's true as well. So another kind of logical statement that I want to talk about is one that's called a tautology. This is a logical statement that is always true. In other words, when you do the truth table, the final value, the end result column, is all T's. So what that means is that the statement is true for every possible set of inputs. An example of that would be something like, let's say, I am wet, or I am not wet. And you can see, just kind of applying the rules of English here, that clearly that statement is always going to be true because one of those statements will always be true. Either you are or you aren't. So that would be an English statement of a tautology, an English example. So let's look at this negation law. And this is actually the statement that I just did in English, converted into a logical statement. This would have been, I am wet, or, and this is the negation, I am not wet. And we want to show that this is, in fact, in logical terms, a tautology. And to do that, we're just going to construct the truth table. And this truth table only has one base column. There's only one variable, the P, in the original statement. So that's our base column here, the first one. Then I've copied the logical statement into the rest of the table. And again, I filled in the P and P columns here where I'm just copying the values over. So let's see how this table works out. The negation has to be done first. That's going to reverse all of the P values. Then here we have this OR. And remember, an OR is false only if both of the input columns are false. And I don't have any here. I don't have any rows where both of the values are false. So this is going to be true all down this final column. And that gives us the end result we were looking for. This statement is true all the time. You see how I've written it here, kind of using the language of equivalences. I have the statement on the left, and I have our equivalent symbol. And then I said that that is equal to true, and this is kind of the way it's written. I did it with a lowercase t that's in bold. That's how I would write that this statement is always true. Okay, well, there's an obvious opposite to a tautology. It's a contradiction. A contradiction is a logical statement that is always false. For example, let's look at the negation that we're going to do here. You can see how this kind of compares to the previous one. If I wanted to use the same I am wet analogy, this would be I am wet, and the opposite of the first statement, I am not wet. Clearly, both of those can never be true at the same time, so this would be a statement that's always false. So let's take a look at how the truth table works out. If I fill in the P's, I didn't do it in advance this time. This one also only has one input column because there's only one variable in the original statement. Now the negation reverses everybody. Then we have this logical and. And logical and is only true when both of the inputs are true. Every other combination is false. And you see I don't have a row that has two trues. So all of these are false. And this is our final conclusion. This is a contradiction. And we write that very similarly. I have the original statement. I have our symbol for equivalence. And here, this is maybe a little confusing. We don't put an F for false. We put a C for contradiction. And the T that we wrote when we're talking about a tautology, for example, this one, don't think of that as a T for truth. Think of that as a T for tautology. So that would be examples of these two classes. Okay, so that's our last slide here. And this is, in fact, our last slide on logical equivalences. From here, we're going to go on and talk about conditional statements, which is really at the heart of math. Conditional statements are statements that have the form if something, then something else. And that's how mathematical theorems are most commonly written.